Okay, this is the fourth video in the Earth series known as Earth's Magnetosphere. So the other three parts of the video series are Earth's atmosphere, Earth's interior, plate tectonics and continental drift, and this is the final video, Earth's magnetosphere. So let's talk about what the magnetosphere is. It is a protective force field like magnetic field that's being generated out from the Earth due to the planetary composition. So let's talk about that. If you remember back to the Earth's interior video, we discussed how the outer core is a liquid metal and the inner core is a solid metal. And due to the rotation of the planet, the outer core, as it's being liquid, is moving freely around the inner core at a fairly fast rate. So this creates a magnetic field. This magnetic field is vital for life, right? Without this magnetic field, life would not be possible on the planet Earth. Let's talk about what it is. Well, it's discovered in the 50s. In fact, we really had no idea. Now, we knew about magnetism. We didn't know that the magnetosphere is this giant bubble that projects into space this large distance. Now, we did not know about that until the 1950s when Sputnik launched, right? This is the Sputnik space probe. Russia launched, first successful space mission ever launched. And it had a magnetometer on it, and it realized that there's a lot of magnetic forces being generated out there, and this confused scientists as, again, it was previously unknown. So what is it? Well, it's a large bubble of magnetic field, right, surrounding the Earth, and it comes to a focus at the magnetic north and south poles. So the magnetic south's about 80 degrees north latitude in Canada, and the magnetic north is in Antarctica. Now that sounds confusing because it sounds like I said it backwards, but I did not. So here you can see the bubble, right, protecting us from the solar wind. That's a critical part of it, right? Solar wind are these high energy particles sent out from the sun. It's really the outer reaches of the sun's atmosphere that can no longer be gravitationally held onto, and it just releases these high energy particles, and they're just ions, right? Lots of electrons just floating around. But the magnetic south pole is in the geographic north pole. This is confusing to a lot of people. And inversely, the magnetic north pole is at the geographic south pole. So this is, again, very confusing to a lot of people, but I'm not real sure why it should be confusing because, as you know, a compass should point to the north. Well, the compass needle north is going to point to the south pole of the planet. So as you're trying to point to the north, right, north connects to south, right, so that would point you in the northern direction. So I think that's very well known, but that's the reason that it points to the north, because north attracts to south, right? So when I say points to the north, I mean geographically, of course. So again, magnetic poles are opposite to geographic poles at this time. So let me just make sure we understand that, because the magnetic poles do flip. So this bubble is further defined into what's known as the Van Allen belts. And the Van Allen belts are these two large donut-shaped bands, right? So I'm not sure why they call them donut shaped. They just kind of look like a big, U kind of thing. I don't know, whatever. That project out into, outer space. And it's a good distance. So, and they're really just giant field lines. And they're named after a famous scientist. I forget his first name. Last name, Van Allen. Pretty easy to remember that. But he's the one that discovered these different belts of magnetic field strength, right? So this one's really strong, and then this one is that right? Yeah, this one's stronger, and then this one's weaker here. But now, when astronauts are in the International Space Station, or they're in the space shuttle back in the day when it was still launched, this magnetic field still protects them from this, right? So this is something that is very helpful to low orbit things like the space station, right? Because they don't have to shield that additionally, because we're still within this reach of the planet to where we're still protected from the solar wind. Now, when the Apollo missions went to the moon, this is a major concern for NASA, because we were afraid that these solar wind particles could possibly have killed the astronauts. So it was not as strong as they were originally thinking, but NASA shielded the spacecraft either way, which is a great call, obviously. And they shielded it by lining the spacecraft, all the Apollo missions, with lead. So they had like a thin sheet of lead built within every part of the Apollo spacecraft, because lead is so dense that it will block these solar wind particles, or at least most of the solar wind particles. So let's see. Let's move on. Van Allen belts do not extend past the moon. So now, another interesting side effect of the magnetosphere is that it creates these beautiful things called auroras. There's a great video linked on YouTube about auroras, so if you get a chance, check that out. So solar wind particles can sometimes overcome the magnetosphere, and this especially happens when the sun is active, right? So in the second semester, you'll see that the sun goes through periods of more activity and less activity, and it's what's called the solar cycle. When the sun's really active, it can produce massive amounts of these electrons, and sometimes the magnetosphere just kind of becomes overcome with them. When that happens, these excess electrons follow the Van Allen belts down into the atmosphere, and it excites the gas molecules, right? And when gas molecules are excited, it creates light. This is how neon lights work, right? If you understand neon gas, when you shoot a lot of electricity into it, it lights up red, right? That should be very well known. Spectroscopy is the entire science that has to do with exciting gases and having them light up in different colors. So this should not be a completely foreign idea to you, as I'm sure you're aware. Also, even the fluorescent lights at school have gases that are excited with electricity, and it produces light, right? So the electrons can fly down these Van Allen belts, and if the solar wind becomes very strong, it'll come down, and it comes down in the polar regions, right, in the North and South Pole, which is the most common places to see the aurora, and it will excite these electrons and generate these very pretty things, right? And they're oftentimes called the northern lights or the southern lights. And the northern lights are the aurora borealis, and the southern lights are the aurora australis. The easy way to remember that is aurora australis is Australia, right? And Australia is in the southern hemisphere. And aurora borealis is the other one, right? Which is in the northern hemisphere. So check out that other video I had on YouTube about that. It's a very cool little, it's basically more of like a light show, but it's very beautiful. I'd love to see one. I've never seen one personally, but I sure would love to. Alright, that's another little quick one on the magnetosphere. So if you have any questions, ask me in class. And I shall see you there.